Okay, so good morning, everyone. Thanks for being here for this doctoral meeting. I have the difficult task of introducing Javier and also to conduct the discussion later, but I think it will be very interesting for all of us because the topic today is a very interesting and quite high impact and a kind of hype area that it's now going on in this topic of quantum computing. So all of you know Javier, so it's not worth to take a lot of time talking about him, but just simply saying that he's pursuing a master in quantum information science, and he's also doing research, his PhD, on this topic of quantum computing, and particularly today he will be discussing about distributed quantum computing integrated in heterogeneous systems. It's maybe all of you know, but if it could be also the case that some of you don't know a lot about quantum computing, so it's a very hard topic, so we hope that Javier at least gives an introduction and some basic ideas about that. I was telling before that 3 years ago in one of the plenary talks in the Artificial Intelligence conference in Malaga within the CEDI, one of the plenary talks was, as far as I remember, by Ignacio Latorre and was about quantum computing. And almost anyone in the room understand a single word after the second or third slide. The faces of all the people were clearly saying that no one was understanding what's going on there. So it's a very difficult topic. I appreciate very much that you are working on that, but of course you have a good supervision in this topic, so we are sure that there will be a very high success in your research. So please go ahead, the floor is yours, and let us know a little bit about this distributed quantum computing area.
Okay, thank you so much, Alberto. Hello, everyone. Thank you so much for staying here, especially at the 10 of the morning on a Friday of July. Okay, I usually when I... Yes, July or November, depends. Usually when I start this type of presentation, I try to present me or present my team, but you are my team. All of you know me. Alberto said that this is a very complicated task, but my idea is try to explain the title. If when I finish my presentation and you go to your homes and you understand the title, I will be a very happy Frank. And okay, I think it's the best idea. Try to explain the title. I go start to define the computation. Okay, it's the first part and the best important part. And this definition is a controversial definition in the bibliography because of all you know. The computation is constantly changing, and our computation is very different of the early years of the computing. But if we focus on the definition of Turing of computational system, a computational system is a formal mathematical system that operates according to a set of rules, and this is very important, over a physical architecture. It's important because if we have a mathematical formula is very good, but doesn't exist any architecture to implement it, we don't have any machine. In the case of classical model, our mathematical formalism is the Turing machine. And the set of rules is moving the head of the controller to the left, to the right, read, put a value, etc. All of you know the Turing machine, I think. And our physical architecture is we have a binary model and implemented using semiconductor technology. In this case, the MOSFET transistor. The MOSFET transistor is very interesting because implement the 0 as the 1 logic, the binary model, using the semiconductor technology, and if you put a negative charge in the gate, you close the channel and doesn't exist a flow between the source and the drain. This is the counterpart. If you put a positive charge, you create a channel and exist a flow between the source and the drain and generate a logical one. In classical computing, we have been increasing certain features of processor to obtain more computational efficiency. Okay, One example is the increase in processor frequency and power, trying to improve the number of instructions per unit of time. This has a physical upper limit, because at high frequencies, the transistors don't have enough time to switch between the logical 0 or logical 1. Another approach has been to increase the number of transistors per chip, improving the processor architecture, and adding more cores for parallel programming. This also has an upper limit, since increasing the number of transistors means reducing their size and the distance between them. Right now, the distance is about 4 nanometers, or about 40 atoms between the transistors. At this kind of distance, quantum mechanics starts to apply, and an effect known as the quantum tunneling appears. This effect allows electrons to pass through the closed channel of the transistor and generate a false one. This is the main problem currently encountered by processor designers, okay, and is our upper limit in this type of computation. Therefore, we need to implement a new model of computation that's emerging quantum computing. In this model, the qubit is our minimal unit of information, as in comparison with the bit in classical computing, okay? This figure shows the representation of a qubit in the well-known block sphere, where each point on the surface of the sphere is a quantum state, okay? For example, this is the classical 0, and this is the classical 1. Okay, this is very good, but what is the main advantages of the quantum model? Okay, one of the main advantages of the quantum model is the use of the superposition, okay? That is, being in two states at the same time, for example, the 0 and the 1. This is what the Schrödinger cat experiment tries to exemplify. If you lock a cat in a box, okay, with a 50% chance of dying and other 50% chance of living, it will be alive and dead at the same time until an observer decides to measure. The measurement is very important in the world of quantum, because is when the quantum state is converted to a classical state, okay? This is called that our quantum state collapsing into a classical state. In this case, collapsing 0 or 1. And is example in a GIF of a superposition between 0 and 1. And in our case of quantum computing, we are going to generate superposed states between 0 and 1, being able to have, for example, 20% of 1 and 80% of 0, for example. And in this case, I showed you a representation of 0 on the block sphere. Here, this is the 0. And a 50-50 superposed state in this other figure. Can we take advantage of this? Well, you might be thinking that quantum has an intrinsic parallelism, like the parallel programming, in being able to work with all possible values at the same time. The main problem is that it all collapses into a classical measure at the end of algorithm, because we need to read our quantum algorithm or our quantum state and transform into a classical state. Even so, different algorithms have been developed that have been able to exploit this feature, okay, and obtain exponential accelerations in time or space complexity. This is the famous case of the short algorithm, because we have the problem of the prime factorization and reduce the complexity from an exponential complexity of time to a logarithmic problem. This type of problem, the prime factorization, is of crucial importance in the world of cryptography, okay? And this is the starting of the quantum computing. On the other hand, go to the part of heterogeneous systems. In the classical world, we have other techniques to accelerate our computation, also in classical. For example, heterogeneous systems. In this, typical, we have a host that will orchestrate the computation among different hardware devices. with specific characteristics such as GPU or FPGA or more GPUs, typically in a supercomputing center, for example. Okay, the main purpose of this is to take our monolithic code, this one, which takes considerable time to execute or memory, and distribute the task between the host and other devices. And we have these red boxes for the communication times that implies overhead in the computation. Okay, so I think a brilliant idea right now is to increase the computationality capacity. Could be to integrate quantum computing as a heterogeneous device. This way, we will be able to run very expensive problems that in quantum are easily accelerated. For example, the prime factorization. And we have for example, in the CESGA, in the Galician Supercomputing Center, we will have a QPU like another hardware accelerator or device. Continue. Another way of computation very known for us, and to speed up our computation, is to distribute the computation in different compute nodes. This is known as distributed computing. We have different computing nodes with the distributed memory, and we have a interconnected network, like, for example, internet, very slow network, or another high-performance link to connect the different nodes in, for example, a supercomputing center. The goal in this thesis is to research the distributed quantum computing with the objective of communicate different QPUs separated in the space, different chips of quantum processors. For this, we can use classical links, for example, to transmit different bits, but we have the node as quantum link. And this is very interesting because these quantum links are related with a quantum feature that I didn't told you about, because it's very complicated to explain at the start of the presentation, which is the entanglement, okay? These features allows that through specific operations over different qubits, we can entangle two qubits in such a way that when we measurement one, for example this, the counterpart, the other qubit, in another different space, is immediately affected wherever it is. Okay, for example, we have this qubit in Galicia and another qubit in Madrid. A very famous experiment for the entanglement qubits is the two different particles in different islands of the Canarias Islands. As you may think, this has direct implications for distributed computing, especially for distributed quantum states. Okay. With all of them, this is all of the title. But I want to talk about different open research lines for my tests for our group. First of one is developing compilers for the quantum software stack, because we need different compilers and high-level languages or assembly codes to program our physical devices for quantum programming. On the other hand, in relate with the heterogeneous system and the integration, we need to improve our integration of QPUs, modifying, for example, heterogeneous frameworks like CiTIUS. And for finish with these different lines, we have the virtualization of physical QPUs, for example, the QPU of the CESGA, and try to virtualize 2, 4, or 8 QPUs to simulate the distributed quantum computing and to prove our different distributed algorithms. Okay. And finally, with the conclusions about the quantum computing, we can conclude that it's a new model of computation. There is a lot of está todo bien, ¿no? Ah, vale. There is a lot of model of computations in the bibliography, for example, the reversible computation. But in this case, the quantum computing allows us to reduce the temporal and spatial complexity of different classical algorithms. For example, the big example of the prime factorization. And about the future of this model, it's not expected to replace the classical computing because we have a lot of problems of the physical architecture. For example, we need very low temperatures very close to the absolute zero. And the idea is to have these different QPUs in, for example, a supercomputing center. And in this case, we can use the heterogeneous systems. And finally, the idea is interconnect different QPUs to achieve a large number of qubits, because at the moment it's very difficult get a big number of qubits in a single chip. And this is all. Thank you so much. And any questions?
Thanks for keeping this short, and now time for questions. So please go ahead. Please use the mic because this will be recorded and we need the voice.
Hello, thank you very much for your doctoral meeting. My question relates to one point of your conclusions, and is about quantum processing units will not replace GPUs for training AI models?
Yes, okay. The current big problem of the quantum machine learning models is change the information in the qubits, okay? We have one characteristic called the decoherence time, and this is the time that you need to put all the instructions in this time. And currently is for 100 microseconds. For change the big data, the big information in the qubits, we need a lot of time. So only for change the information in the qubits. So at this moment, it's impossible to generate a real case of quantum machine learning.
Okay. And when will quantum processing units become available commercially, like GPUs are now, currently?
Oh. This is predict the future.
Yes, but
okay,
maybe a range, like
okay.
10 years, 20 years.
Yes, I don't know. when I studied the degree in computer science, I don't think that in 5 years we have a QPU in the Tesla. And in 5 years we have this QPU, and I don't know, maybe in 5 years in the future we have our QPU in our personal computers, but I think in 5 years, no, probably, but I don't know. Okay. This is a recording, and in the future the people will say me.
Okay.
Discuss it together.
Yes, what's a nice presentation. I have to ask you for some memes to add to my presentation.
No, I would like to say that one more meme.
Yes.
No, next. At the end.
One of the things you forget to mention is that the real problem right now with quantum computing is noise.
Yes.
Quantum computing right now are quite useless because the qubits are too sensitive to any change of temperature. Even the cosmic rays affect the qubits, so you can run a quantum program that lasts more than few microseconds because the quantum state collapse and the noise run all the result. So you ask when we are going to have a commercial QPUs. There are commercial QPUs. In fact, the Telga pay for the GPU,
pay a lot.
So they pay a lot. It's a commercial device. But the real problem is the answer is when researchers get a fault tolerant QPU. Now there are some algorithms for mitigations for mitigate the noise. So try to reduce the effect of the noise over the result of the computation. But this is not enough. We need a fault-tolerant quantum computer. IBM, that is one of the companies that have more importance in this field. In the roadmap, said that about 2033 or 34, they are going to have, they plan to have a QPU that are fault tolerant with more than 10,000 qubits. If this is true, it could be in, let's say, 10 years that we can start to talk about the really useful quantum computers. But it's, imagine that we are in a point that is similar to the classical computing in the middle of the 20th century. Nobody think that in 50 years there were personal computers. There are people that say, oh, nobody needs a personal computing at home. Why you need a personal computing at home? No. Yes, yes, yes. That's Bill Gates. Say that you don't need so many RAM, you don't need. But we are now with our mobile phones that are more powerful than the ENIAC or any computer in the middle of the 20th century.
So you can see a future where we can have some of these GPUs in our laptops or devices?
I don't know. It's like we have. I don't think it's because I think that the algorithms that can be ported to a quantum computer are limited. It's not like a general machine. It's not like a general purpose machine. I mean, to make an operation like the product of two integers is quite slow in a quantum computer. Have no sense to make the product of two. You can do that. You can do that.
Will be that will be available in supercomputing centers or on
Yes, probably.
Not typically in a laptop or
No. There are some. There are even more mobile phones from Samsung that incorporate some quantum technologies, but to generate random numbers. It's not a quantum computer; it's a quantum random number generator. And so for security aspect, even for communication with the quantum internet, we probably have to maybe devices that incorporate some quantum effects to connect us to the quantum internet. But for computing, I don't think so. I think that is going. It's like a FPGA. We have a FPGA in our systems.
Yes, I totally agree.
Probably not. I don't know. Maybe Silvia can say anything more. So I see more.
Thanks, Thomas.
FPGA than like a GPU.
Thanks for the contribution. One question here.
Thank you for your presentation.
Thank you.
It's nice. A question is about the cryptography.
Yes.
I think that is a topic in which quantum computing may be useful.
Yes.
How do you see in near future the algorithms that
Yes.
we trust on them now?
Mhm.
How much time, more or less?
It's a problem because when the quantum computing exists and doesn't have any errors, the only persons to use the new quantum algorithms to cryptography is the same people that can exploit the classical algorithms of cryptography. No? But in this case, and currently we have algorithms using classical computing very strong with respect the quantum computing. For example, the elliptical curves. I don't know a lot of this topic, but I know that exist different solutions in classical world currently, but I don't know if in the future other short person implement other algorithm to exploit the classical algorithms. In any case, we have algorithms in quantum world to cipher information.
Thank you.
Thank you, Kaba.
Thanks. I was curious about a couple of aspects of your presentation. First is, what is the current state of your research? So in your research plan, at
Yes.
what point are you now? And also, what are the areas, the algorithms, the topics that could take advantage of this distributed quantum computing approach?
Yes. In my thesis, the point currently, well, the last year I with Thomas and the other mates, we prepared different reviews of the state of the art. For example, distributed quantum computing or the quantum compilers. But in my case, I work in develop new approaches in the quantum software stack. For example, develop new compilers, develop new intermediate representation that is very important in the world of compilers to facilitate the task to implement new compilers. And in the future, we can try to make a simulator for distributed quantum computing.
And what areas, what algorithms, what research topics will benefit from that?
Okay, for example, exist different quantum algorithms for distributed computing. For example, exist the short algorithms in a distributed form. And if we can implement the virtualization of physical QPUs, you can run this in the CESGA, for example, and try to extract different results for example, efficiency in a real computer and not simulated.
Yeah, I know not an expert in this area, but what I can see from my views that, for example, some people talks about machine learning, quantum computing, and so on. But at the end, there are not these heavy algorithms that need a lot of distributed computing or lots of power for doing that, because at the end what they do is very simple things, very simple classification problems or that. This is why I was interested in knowing which area could benefit from that.
The benefit of this research is all of the algorithms benefit of, for example, improve the integration of the QPUs in a framework like a SQL. Because if you have an algorithm, you can implement inside your hybrid computation.
Yeah, that's a smart approach. You provide the technology for doing that, and the people who develop the algorithm who could benefit from that. So it is agnostic in terms of what algorithm could be used for that. Okay.
I provide the tools, and you have the algorithm.
Any other question, remark, contribution? Nothing? Coffee?
Coffee, please.
So thanks, Frank, again for your talk. Let's
Thank you so much for
give you an applause. And see you next time in the next doctoral meeting we will have. I don't know when, but probably after the holidays.